Next thing we want to talk about are diagrams. Now there's some general themes that I'm going to share with you, and we're going to make decisions to apply particular labels and go in particular directions. There's no hard and fast industry standard here. There are some general rules that everybody follows, and there are some certain things that some people like to go in one direction and some people like to go in another. So if some of the things I say and some of the things that Ron say don't quite line up perfectly, okay, that's okay, because like I say, there's no hard and fast rules. I'm going to provide you with my list of hard and fast rules, and we're going to do our best to follow those rules throughout the course of the term so that, you know, when there's a decision to make to go left or to go right, hopefully we will have already addressed that and made a decision to go in a particular direction. Like I say, Ron may have experience and particular reasons for wanting to go in a direction that doesn't quite line up with what I'm suggesting. Okay, labeling is a big thing because I have 3 diagrams that I want to teach you, and there's not even necessarily industry consensus on those names. Okay, for example, but we're gonna provide a set of rules. Ron may suggest that they are my rules and arbitrary, but it works best if we have a set of rules to work from as we move forward. Okay, so 3 different kinds of diagrams. The first one is what I call a wiring diagram. So what is a wiring diagram? A wiring diagram, first of all, shows both circuits. So I just showed you the fact that there are 2 circuits. The wiring diagram is going to include both. Okay? The wiring diagram indicates in some form, it's probably not exactly to scale, but it puts a good deal of effort into indicating physical locations. So when the wiring diagram shows a wire going to connect to a particular device, it puts a little bit of effort at least into talking about where you find that device. Okay? Particularly when you have multiple wires going on a device, they're going to all go and congregate in the same place on the diagram. Okay? It shows all connections. That may seem strange. You would think all the diagrams would show all the connections, but that's not really true, particularly in the sense that this diagram shows both circuits and all the connections for both circuits. Some diagrams will completely choose to ignore one circuit or the other. So this is a true statement. It's also probably one of the greatest weaknesses of the wiring diagram. The fact that it has a lot of detail. On the surface, that seems like a good thing. Well, the more detail, the better. Give me all the information I need. The reality is, I'm going to have you draw some wiring diagrams for me, and you're going to discover fairly quickly that they get crowded. Because they have a lot of detail, there's just a lot of information crammed into a space, and it gets pretty busy. Okay? So that's the downside, is can become crowded and confusing. Okay, because there's so much detail there, sometimes it just looks like a bowl of spaghetti. Okay, there's lines going everywhere. Okay? Which ties into, by the way, the numbering systems. When we get to the conversation about numbering systems, that's going to help us keep track of what's going where. Okay? Has a lot of detail as a positive, but the flip side of that, the negative, is that sometimes it becomes crowded and confusing. Which is why we have other diagrams that start to pull details apart and make it easier for us to see what's what. Okay? So let's look at that next. Actually, before we move on to the next diagram, let's take a moment and look at what we're going to be using for our wiring diagrams this term. So what I'm showing you here is the template that I will provide you guys with, and you will be filling in all of the wires that connect to all of these locations. Okay, so up there in the top left, you can see line 1, line 2, line 3, and neutral. Okay, so that provides us with all 3 phases of a 3-phase AC circuit. We're not going to be using that at all right now. We're actually on a DC motor, so that's not shown on here, but I may add that if I get a chance to get you your DC power. Okay, but we're going to use the line 1 and neutral to get our single-phase AC power, because that is where we're going to feed our control circuit from. Okay, so the control circuit is going to be 120 volts AC. It's going to come from right there. The DC power for the motor, I'll add a couple of blocks in there so that you can show where that power is coming from. Then below that, that row of rectangles, you can fill in the labels in there from the terminal block, whatever terminal blocks we're using to connect things like start buttons and stop buttons and whatever other control devices we might be using. And then on the right side, this is the motor starter, which Ron's going to talk about on Wednesday. And you can show exactly how you wire up the motor starter. Okay, so you see what I mean about physical location. It's not to scale in terms of exactly what the lab station looks like, but it shows us the actual motor starter, the way it appears, where you can find those terminals to make those connections. Okay, so that's the template. We're going to be filling in, creating these wiring diagrams using that template. Okay, let's move on. So the next type of diagram is probably the most important one for us. It is the ladder diagram. Okay, and the ladder diagram, aka, okay, also known as, often referred to as, the control diagram. So you can probably guess what it does. Is it shows the control circuit. So here we go. We are going to ignore the power circuit. We're going to forget about the fact that we're trying to control a DC motor. We're going to focus exclusively on how we control it. What wires go where, what connects to what, so that we can turn this motor on, turn it off, make it spin backwards, whatever it is we want to do. Okay, so this is just the control circuit. Okay, now, before I go on with my list, let's start drawing a ladder diagram. So why does it look like a ladder diagram? Or sorry, why is it called a ladder diagram? Because it looks like a ladder. So here's what a ladder diagram looks like. We have a rung here and a rung here. Sorry, those are the rails, I suppose, and there are the rungs. Okay, looks like a ladder. We start up here. Let me put in here my fuse and my disconnect. Add our power supply, 120 volts AC. That's what we're using to control our control circuit, to power our control circuit. So 120 volts there, that's line 1. Over here, that's our neutral. Okay, so right now what we've drawn is a whole bunch of short circuits. All right, so we better fix that. All right, what I'm going to do is I'm going to put a switch there, and I'm going to put some kind of a load over there. Actually, maybe let's, before we go any further, let's call that a light. Let's turn on a green light. Okay, so there we go. That's the first rung of our ladder diagram created. We have a switch, and that switch controls a light. Okay, so this is the way we draw our circuit. Each part of our control circuit just is shown on another rung of our ladder diagram. Okay, down here, that is a normally open momentary push button. So last week Ron talked about switches, push buttons, all kinds of different control devices. There's a momentary push button, okay? And let's use that to control a red light. Okay, so there we go. We've got the start of a ladder diagram. Okay, so let's go back here and talk about some details. So it is meant to be clean and neat and tidy. Okay, so unlike that wiring diagram that gets really messy really fast, okay, we are going to keep the ladder diagram neat and tidy. Things don't start getting all jumbled together and all crowded into one space. We just keep, every time we have a new idea, we build a new rung to our ladder diagram. I've worked off of ladder diagrams that when they are printed out, they're 80 pages long. Okay, just keep adding another rung. All right, so it doesn't add any mess to the existing idea. We just get new ideas and move on to the next page and just keep building, add another rung to the ladder. Okay, so stays neat and tidy, clean and neat. The way we accomplish this is that there is no indication of physical location. Okay, where stuff actually exists in real life on the lab station, we don't care. Okay, when we're drawing the ladder diagram, that doesn't matter. Okay, for example, I'm going to have to skip ahead a little bit again. Ron's going to be teaching this on Wednesday, but if we eliminate those lines and say, no, that's not a pilot light, that is in fact a cube relay. And a cube relay, that was the thing that, well, I call it a motor starter, but a cube relay functions in the same fashion. We can create that magnetic field by putting current through that coil, and it will pull levers open or closed. It will toggle contacts. So down here on the next rung, I could draw a normally open contact, and right here, now I draw my red light. Okay, functionally nothing has changed. Before we pushed the push button and it turned on the red light. Now we're going to push the push button. It's going to energize the coil of the cube relay, which means it creates a magnetic field. That's going to take this normally open contact and it's going to pull that contact closed, which means that is now going to turn on the red light. So functionally we haven't changed anything. Push the push button, the red light comes on. Okay, but we've added an extra step. Okay, we now have the push button doesn't directly turn on the light. The push button energizes the coil, which closes the contact, which turns on the light. Okay, all kinds of good reasons for doing that we'll get into later. The point I want to make right now is that this load located on this rung of the ladder diagram and this contact located on the next rung of the ladder diagram actually both exist within the same housing of the same cube relay. We call them a cube relay because they're about the size and shape of a big ice cube. Okay, so both of these things exist right inside that same device, and yet they are completely pulled apart here in the ladder diagram. Okay, so that's how we keep it clean and neat. Is we're interested entirely in just the circuit and how the circuit functions and how we wire it. In terms of actual physical locations, we don't care. Okay. I guess the only other thing that I want to put here is things like pilot lights. Okay, and I've already drawn them here in the ladder diagram. Okay, so the ladder diagram is the control diagram. It shows the control circuit. Okay, pilot lights don't actually play a role in controlling the motor. Okay, but we absolutely include them on the control diagram. Pilot lights are included because they are a very important part of the control process. Okay, go back to the reason we're doing all this again. We've got a controller sitting up in a control room, and he's a very long way away from the motor. He pushes the button to turn the motor on. How does he know it turned on? He can't see the motor, he can't hear the motor, it's a very long way away. The only way he knows the condition of the motor is through any information we might provide him at his console. Okay, and that's through pilot lights. All right, so we have pilot lights that turn on and turn off with the motors, okay, so that we can provide feedback to the controller so he or she knows the status of the motor, whether it's on or whether it's off. Okay, so the pilot lights don't specifically control the process, but they're absolutely part of the control circuit because they are fundamental in the controller being able to control the motor. How many times can you say control in one sentence? Okay. I'm going to come back. I've got a list of details, a checklist for every time you make a ladder diagram to ensure that you provide all of the right details. Okay, but I need to teach you those details first. This is very far from a complete ladder diagram. There's all kinds of stuff we have to fill in here yet before it is complete. Okay, but let's work our way through what all those items are before I provide you with the checklist. We'll leave that to the end. The next diagram, the third diagram, is the power diagram. So we started with the wiring diagram, which has everything. Then we looked at the ladder diagram, which looks at only the control circuit. So now we have a power diagram that looks at just the power. Okay? So it shows the motor circuit. Okay? So when I started the conversation, I just drew the one little circuit, DC power supply and a motor. So essentially that's what the power diagram is, but there are some other items that we better include. Okay. There is little indication of physical location. So again, like the ladder diagram, we're not too concerned about where things actually are. We just want to know how they are connected together. Okay? So shows circuit. This basically just lists the details that we have to include through the motor starter, which you will learn about soon enough. Motor starter, actually let's put motor starter contacts and overloads. Okay, so those are things that you're going to learn about on Wednesday. Okay, but that's really all the power diagram includes. So I could say that we have, let's say we have 60 volts DC as our power supply. We can down through a contact, okay, a couple of contacts, maybe if we're going, there's reasons for doing this, which we'll get into later. Controls both the positive and the negative lines of our DC circuit. And then we have these things called overloads, which which protect the motor. And then we come, and there's our DC motor. That is a D, believe it or not. Okay, and that's a very simple power diagram. Okay, not much to it, but that'll do it. Okay, remember, like I said, this term we're going to spend an awful lot of time focusing on the ladder diagram as opposed to the power diagram. Okay, much more focus on the control circuit. There's a lot there that we can do. Power circuit, in many ways, is that and will always be that. Okay, it's not quite true. There's definitely more to it, but got a long way to go before we get to that point. Numbering and labeling. So I said when we looked at the ladder diagram that it was very incomplete. And this is what it's missing. It's missing all the necessary numbers and labels so that we can tell what's what. Okay, when you start to get a ladder diagram that's very long, lots of different rungs, pages and pages, maybe even hundreds of pages in length, you need to be able to keep track of what's what. Okay, and we do that through numbering and labeling. So the first thing we number are the lines or the rungs of our diagram. So we have line numbers. So let me go back here and draw the ladder diagram again. Okay, so that's not exactly as I drew it before, but that's a nice little diagram that we can start with. So first thing we need are line numbers. Okay, so we start at the beginning. 1 is 1, 2 is 2. Okay, there's lots of different rules that you might choose to follow. Typically, you might see these labeled 10, 20, 30, 40, 50. And so if later on they want to make an addition and they want to come back and add a rung in here, they don't have to change all of these rung numbers. They can just slide in here. So if this was 10 and 20, they could just slide in here and create a rung 15 at some time in the future, and it doesn't destroy the numbering of everything else that they've done. Okay, so doesn't really matter. Okay, we're probably not going to bother, but that's something that would not be at all uncommon for you to see. Okay, sometimes they even start at 100, 200, 300, and that gives them room to put 100 rungs in between if that becomes something they decide they need to do down the road. Okay, so that's where we begin, rung numbers. Next is wire numbers. This one takes a little bit of figuring out, but once you understand what you're doing, it becomes extremely helpful. So, for example, for the groups that were with me last term, right at the end of the term, we did a couple of simple signal labs, fairly small, something almost exactly like that. and even at that, it became obvious really quickly that it's hard to keep track of what wire is what. So if we actually wire the numbers, okay, if we've got, these are all single conductor wires that we've got spread around our lab station, and while these two items might be together right in the same place, some of these things may be a very long way away, especially in the case of the real world application where one wire goes from the control console in the control room across the plant to the motor starter at the motor. How do you identify what wire is what? Okay, and we do that by numbering the wires. We will actually attach numbers right onto the wires. Okay, so how do we do this? Again, the actual number doesn't matter, okay, but we're going to start at 1. All right, so the first wire that we see is right here, is wire number 1. Okay, so that wire is going to get assigned the number 1. Okay, any wire that is actually attached to that gets assigned the same number. Okay, so the question is, when is this wire going to be 120 volts above ground potential? And the answer is the whole time the lab is turned on. The lab station is turned on, the circuit is energized, we close that switch right there, there's 120 volts at that wire. Okay, where else is that true? At the beginning of every single rung, which means this wire right here is also wire number 1. If we drew a third rung on our diagram, we'll put a normally closed contact there, make that a red light. This is also wire number 1. They are all at the same potential. They all have the same voltage on them at the same time. Okay, anytime the lab station is turned on. Okay, they're all wire number 1. Now, as soon as we go across a device, we need a new number. It's a different wire because it behaves differently. It has voltage on it at different times. Okay, makes sense, right? Here, there's no voltage on this wire until we push the button and close that contact. So that's across a device, has to be a different number. Same thing here, until that contact closes, there's no voltage here, across a device, a different number. Here, this is normally closed, so there is voltage across there right now. There's voltage here, same as here. Okay, but when that contact opens, whenever that's going to happen, there's still voltage here, now there's no voltage there. So once again, it behaves differently. To cross a device, we need a new number. Okay, so this is wire number 2. Okay, which means the other end of that wire here is wire number 2. All right, on a small diagram like this, we probably only need to put that number on there once, but in real life, in your lab, you're going to have to do that at both ends of the wire so you can keep track of the wire here and the wire there. Now, we'll go across a device. We can call this wire number 3, or we can label it N for neutral. Commonly, this is going to be our white wire. We're going to label it neutral. We could call those N. So this is where numbering / labeling. Sometimes we mix and match a little bit. Okay, for the time being, let's call that wire number 3. Okay, but we could label it N. Okay, so same thing here. These are all neutral wires. These are all wire number 3. Okay, so now let's come down here. We've got the second rung. Here's wire number 1 attached to this normally open contact. On the other side, we have a different wire. What number should we assign it? And the answer is it doesn't matter. We can call it 427 if that's what we want to do. Okay, let's choose not to. All right, we just need a new number. Well, where did we leave off? We've used 3. We can't use number 3 because number 3 has a specific function. That's our neutral. So we have 4 available, so let's use it. So that's wire number 4. Okay, and down here, again, this is across the contact. It's a different wire. Okay, we can't use 4. It's up there. We're left with 5. And so we're going to call that wire number 5. Okay, so the actual number that we assign, the label that we give any given wire doesn't matter. Okay, what matters is to keep track of what wire is the same wire and what wire is a different wire. Okay, wire numbers. And finally, the third one is going to be device numbers. And here's where we're really going to get into labels. Okay, so coming back over here, I'm going to grab a different color. Here's a normally open momentary push button. Okay, we know that we have a wire number 1, which is coming right from our power supply, and it's going to attach to this push button. Okay, we need to label this point. It's going to go on one of these terminal blocks. Okay, and what's the label? Well, I will provide you with that information as well, but for the time being, I'm going to let you know that we would call this D11. That is a label on a terminal at your lab station. And this left-hand side of this push button is already pre-attached to this terminal with that label. Okay, and the other side of that same push button is connected to D12. Okay, so we have to put these labels on here so we know where wire number 1 goes. Okay, the other thing, let's follow wire number 2. So this is the coil of our cube relay. For those of you who were with me last year, you already know that the coil of the cube relay is attached to what pin numbers on that cube relay. I'm going to pause, let you guys dig back into your memory banks. Can anyone recall that it's pins 2 and 7? Okay. This is information that you guys are going to get into, and you're going to get really comfortable with this. But here's the point. When you're working at your lab station, when you're trying to decide what to do with a particular wire, okay, I can say I'm holding a wire in my hand and I'm going to connect that wire to D12. What do I do with the other end of that wire? Well, the answer is, if you've connected one end of that wire to D12, then label that wire 2 and attach the other end of that wire number 2 to pin 2 of the cube relay. Okay? And so if you take the time to put that information in the diagram, when it comes time to build the lab, your thinking's already done. Just follow the information in front of you. Okay? If this is a normally open contact, oh yeah, I better do this first. So it's kind of part of this conversation. It's really not. It's these terminal numbers that is what I'm talking about here. But the other point that I need to show you, and there's a couple here actually, but what is it that causes this normally open contact to close? Okay, and the answer is energizing this coil. Well, this coil we have labeled CR, so I must label this CR. Okay, so now I know that when we energize this coil, it causes that normally open contact to close. Okay, the other thing that I'm going to do, and this kind of goes back to the line numbering conversation. This is a reference number. Maybe I should say there are 4 numbering rules and call the reference numbers a different one. Okay, but we need to put a reference number here. So I'm looking at my ladder diagram, and I see here that when this happens, we energize the coil of this cube relay. Well, my question is then, what happens? Okay, what does this control? And so I'm going to put a reference number right here, and I'm going to put a 2. Okay, which means I need to go to rung 2 and find out what happens when this cube relay gets energized. When we create this magnetic field on rung 2, there it is, CR, this normally open contact closes. Okay, if we follow this through, and this is also CR, although it wouldn't have to be, okay, I could draw more rungs here and we could energize other cube relays, call it CR2, CR3, CR10, okay? Or maybe it's MS for motor starter. But now I've got something happening on rung 3. I also put a 3 over there. So I see this cube relay energizes. I've got to go to rungs 2 and 3 to find out what happens. I'm still not quite done. In electronics last year, you learned the notion of NOT. Okay, you did NOT gates, AND gates, all that kind of stuff. If I say this is NOT 3, before I even go to rung 3 to find out what's happening, I know that I'm going to find a normally closed contact when I get there. So 2 means I find a normally open contact on rung 2. NOT 3 means I find a normally closed contact on rung 3. Okay, so those are my reference numbers. That's how I figure out what's happening here, there, and everywhere. Okay, so the conversation started with the fact that I have to label this so that I know that this is controlled by this. And then I have some cross-reference numbers that show me where I go in the ladder diagram to find out what's controlling what. Okay? So just to finish the device numbering, if this normally open contact is part of this cube relay, the pin numbers are, I'm going to ask you to test your memory a little bit more. So pin 1 would be one of the commons. And this is what I always struggle with. I'm sure, let me see, can I get this right? I think 3 is the normally open. And so down here, this could also be that same common 1 with the normally closed contact, which is 4. I always have to double check myself on that. The 4 and the 3, I might have gotten that reversed. Okay? Might be wrong, but that's how we finish labeling. And there's also here, and I'm not sure what it is, the D11 and the D12 is something and I'm not even sure I got those right. I think I did. But there are also labels here where you can connect to the terminal block to get, I think this is going to be PL for pilot light, I don't know, B1, PLB1 and PLB2. Again, those might not be the right terminals, but that's the idea. Those are the kinds of labels you're going to put there, so you know where to put wire 4, you know where to put wire 5. I will provide you with that information well in advance so you can fill in those details while you're developing your diagram in preparation to build the lab. Okay? Ladder diagram checklist. So here, this is it. I'm done from here once we get through our checklist. So, first of all, I'm not even going to number this. This one's just a star. Neatness. Keep it neat, please. Put some effort into straight lines. Okay, I try my best. If you need to use a ruler, please do so. The ladder diagram is intended to be as neat and tidy and readable as possible. First thing you put on your ladder diagram is the supply lines. Almost doesn't need to be on the checklist because you don't have much of a ladder without your two horizontal lines. Second thing you need are your supply labels. What is my voltage? 120 volts AC is the voltage I'm using for my control circuit. Must be there. Third item, the fuse and disconnect. So that's what I keep putting up here in the top left corner. Let me blow it up a little bit so you can see it. There's a fuse and there's a disconnect, okay? And in the disconnect, again, that Ron showed in the video that blew up on the dummy, that housing probably had the fuses right inside. So this would be all one unit. One question that I often get asked is, does it matter which you put first, the fuse or the disconnect? And I'm not sure if there's a set rule anywhere. I've never been able to find one. I don't care. You're putting the two of them in series. What does it matter which one comes first? Okay, fuse and disconnect, always in the top left corner. Next one is kind of like showing the supply lines, almost goes without saying, but you need your rungs. Okay, this is the bulk of your diagram, the body of your diagram, each rung, each part of the circuit, what's happening. 5, and I haven't shown this yet, so this is why my checklist is important. Dots for connections. So every time you have a connection, you must have a dot to show that connection. Okay? I purposely left it out until this point to have this conversation about it. Please do not leave those dots out. They're easy marks for you to lose, and you will lose marks if you forget your dots. Okay? So here's the thing. It happens very rarely. In fact, I would suggest it should never happen. Well, that's not true. It might. Very rarely on a ladder diagram will your lines cross. Okay? In a wiring diagram, in a power diagram, well, probably not in a power, well, yeah, no, absolutely. Power diagram, they do cross as well. Wiring diagrams all the time. You have wires that cross. Okay? That used to be shown like this. There's what you draw when wires cross, to indicate that they're not connected, they're just two lines that are crossing on the diagram. Okay, but again, that can get messy, and we're trying our best to keep this from getting messy, and so we don't do that anymore. Okay, if you see that, those are just two lines crossing in a diagram. There's no wire connection there. There's no electrical circuit being connected there. They're just lines that cross on the diagram. If you want to show a connection, an electrical connection, you must add a dot. Okay, so this is an electrical connection. Those are just two lines crossing in the diagram. Okay, so dots for connections. Make sure you include the dots in your diagram. 6. Where are we here? rung numbers. Okay, so these are the 1, 2, 3 rungs. 7 device labels. Okay, the only device label I would suggest we forgot is we probably should have given this push button a label. Let's call it start. I don't know. Okay. But also things like the CR. Those are really important labels so we can do our cross-referencing in our diagram. And 8, and I'm done. These are the reference numbers. Reference numbers. So that's these numbers over here, saying that when we have a coil, what contacts does it control? Well, that's where we go to find them, rungs 2 and 3. Okay, and I'm going to shut it down there. That's a lot of information. This is the kind of thing we're going to do week to week to week. Okay, you're going to have to be able to read a ladder diagram, but you are also going to have to be able to create them. That's going to be the skill that we want to build. Okay, before you build your diagram, you must spend some time with a piece of paper and a pen deciding what that circuit is going to be. Okay, before you can build a circuit, you must draw the diagram of the circuit. And that'll do for now.